But if at any moment you want to know about your grade, you can see me. It's not like I'm ever wanting to hide something from you. And if I have your labs done and it's a lab you're asking about, I'll tell you. I need a couple more days to grade it. But on regular assignments and stuff, you can always check in to see how your grade is doing. That's fine. Okay. So let's start today's lesson on acceleration. Now, this is really an important lesson. Probably the most important lesson of the entire year. The entire year. Which is crazy to actually make a statement like that in class. And I'm not going to make that statement again. There are other lessons that are going to be real important. This is probably the most important of the entire year. And your physics career going forward. And I know it sounds really like, oh my gosh, it's like a lot of weight right to the rest of your shoulders. But rest assured, we're going to spend a lot of time on this lesson, and you will do fine with this. But the idea behind this extends to all types of physics going forward. Whether it's electricity and magnetism and it's an electron going to a particle accelerator. Whether it's an object like a truck moving down the road. Whether it's energy problems with a skier going up and down the hills. The concepts of motion and acceleration play a role in pretty much every topic we're going to look at this year. Okay, when we get to forces, we'll see how forces, F equals ma, is related to acceleration. So without acceleration, the world wouldn't be an interesting place. Think about it for a minute. If there weren't acceleration, you couldn't even move. My current velocity is what? And now I suddenly have velocity, right? So I must have accelerated. And we're going to talk about acceleration and its definition. We can go to the next slide to see that. And its definition is the rate at which your velocity changes. The rate at which your velocity changes. Delta V over delta T. Delta V over delta T. V minus V0 over T minus T0. But again, if acceleration weren't a real thing, if we could only move at constant velocity, we wouldn't exist. Because we couldn't physically move then. Think about that, right? You can't move unless you can accelerate. To accelerate, you need forces. You need friction in the floor to push off, to accelerate. Imagine playing sports and you weren't allowed to accelerate. I mean, obviously it wouldn't make sense because you couldn't move again, but like just small things. Like I was watching the Yankee game last night, and anyone that's a Yankee fan knows Didi Gregorius at short made this stab in the ninth inning. It was an incredible catch. I mean, the ball was ripped up the middle, and he out of nowhere just sprung to the left and dove fully out and caught it. That's acceleration at its finest, right? That's the concept of you're not moving, you're not moving, you're not moving, and then suddenly you have this quick twitch muscle that pushes in that direction to accelerate. So acceleration is key to any motion in real life. Again, constant velocity, sure, it makes the problem easier because everything is constant. It's easy to look at. Acceleration just makes things a little bit trickier. Now, let's look at the units for a moment. You notice I put 2 units there. The first unit I write is the exact unit from the formula. Well, the numerator is meters per second. The denominator is measured in seconds. So this is meters per second per second. Jot that down real quick. I know it sounds weird, but that's what acceleration really means. It's meters per second per second. And the way I think about that, the way I think about that is this. Meters per second per second. This is my change in velocity, again, over time. Meters per second is velocity. Per second means as a function of time. So what is acceleration really? Acceleration is how much your velocity changes every single second. So let's take a look at an image of this so you guys can see it a little bit better on the next slide. Okay, let's quick image of this. So we've got a car traveling at time 1, and the velocity is 15 meters per second. But then at time 2, which is 5 seconds later, its velocity is only 5 meters per second. Now bless you. So how much velocity did it lose? From 15 to 5, how much velocity? Over a time period of 5 seconds. So every second, how much velocity did it lose? Lost 2 meters per second every second. It lost 2 meters per second every second. Look, it lost, negative opposing, 2 meters per second every second. So acceleration is physically telling you, all right, my velocity is 15, my velocity is 13, 11, 9, 7, 5, and there I'm at 5 seconds later. So every second along the way, this object lost 2 meters per second. That's what this physically means right here. Notice that acceleration can be negative, so it is what kind of quantity? What quantity do we call that? A vector quantity. I know the word isn't there. A vector quantity. A vector quantity. So acceleration, direction matters. direction matters. And we're going to delve into that a little bit after we take a quick look at an example. Okay, we'll get a look into how acceleration direction matters. So let's start with this simple example. Again, for all these problems, the problem-solving technique is list the givens, list what you're looking for, write the equation you're going to use. Now, luckily enough, as of right now, you have only two equations. You've got the velocity equation from last chapter, and now you've got the acceleration equation from the last slide. Because this problem asks about acceleration, you're most likely going to use the acceleration equation. So, not much to really choose from here, because there's really only one equation to choose from the previous slide. In a couple examples or so, we're going to get through where we have a couple other equations to choose from. But for this problem, work through it on your own real quick. List your givens, list what you're looking for, use the previous equation, and go through the process here. Okay, so again, list your givens, list what you're looking for, write down the equation from the previous slide, and practice going through the solution. Use your units to help you so you know what's happening in this problem. I'll do it also, but I'll delay my work. So if you want to look up every couple minutes to check your work, or every 20 seconds to look at your work. Feel free to color code stuff in your notes, right? That might help you this year. I think it's a really good technique. I notice a lot of students do it, and now with notability stuff, or highlighters, you can bring colored pencils. You can really help yourself by color coding certain things. So I've listed the givens on the page, and then I recognize that it said how long will it take. It doesn't directly say find the time, but when it says how long will it take, how long is time, versus how far will it go. That's displacement. Maybe jot that down if that helps on the side too for problem solving. How long will it take versus how far will it go are two very different questions. How long will it take is time. How far will it go is displacement. So again, I've got two formulas to choose from. I could go to last chapter and look at this one, which was delta x over delta t. Or I can use this chapters and use delta v over delta t. Now, because I'm clearly working in this chapter, or this section rather, we're going to most likely use the bottom one. But it also makes sense not to use the top one. Why can't I use the top equation? Why do I have to say, oh, hell no, I'm not using that equation. Why do I have to say that? Yes, correct. Nothing about position. So right away you can't use it. What else? Yeah, the first equation is only valid for constant velocity. Maybe you jot that down somewhere. That this equation can only use for constant velocity. So the minute you have acceleration, you rule this equation out. Throw it out the window. It's done. There's no chance of using it. And the minute you have acceleration, you can't use that equation. The three equations from this section are all going to involve acceleration because we're looking at the topic of acceleration. Okay, so the old formula is worthless right now. So we know we're looking for t. I wrote down delta t in the formula. Well, if we start this problem in the beginning, what can we call t0? 0. Whenever you start a problem that doesn't give you an initial time and a final time, call t0 just 0. Say it started at 0 seconds, which makes sense logically. Ready, set, go. You start the race, no time has elapsed until you start, right? So for these problems, when you are subbing in, we're going to have v minus v0 over t minus t0. You can absolutely drop off the t0 for a lot of them. Because a lot of the problems will just give you a duration of time. So you assume you started at 0. Okay, if it says 10 seconds have elapsed, make this 10 minus 0. Now, we don't know how much time has elapsed. We're trying to figure that out. So we need to solve for t. Algebraically, what's the quickest way to get t by itself here in this equation? Yeah. A and t can switch spots. And again, The math behind that needs to be known in this course. All I'm doing is multiplying by t and dividing by a at the same time. It doesn't make sense in a physics course to show every single step of algebra along the way. Because for the most part, you've recognized that these kinds of tests, subject test, AP test, they're very time sensitive. Because physics is the kind of test where if you don't know it, you've got to think through it, right? You've got to think through the process, which takes time. So save time anywhere you can. So anytime you have an equation that's triangular like this, or even a proportion, you can always switch diagonally. You can always switch diagonally. And that comes from math in like 7th grade. You learned that actually. It was called the product of the means equals the product of the extremes. Probably not even ring a bell to anybody. That is what you did then. So switching diagonally is okay because you're just really dividing and multiplying at the same time. And then we just plug in. V initially was, V final is 0 because this object comes to a complete stop. Right? A complete stop means that the velocity at the end, v, is going to be 0. It's going to be 0. Now recognize, my acceleration was negative. I'm going to get 0 minus 9 meters per second all over negative 1.8 meters per second squared. And that makes sense. Negative divided by negative yields a positive. Write it down if you didn't write it down last class. Time cannot be negative. You're never going to get an answer where time is negative that's reasonable. What do you do if you do? It'll be a quadratic. You get 2 solutions. And you reject the negative solution for time. And you can absolutely get negative displacement, because we've talked about displacement being a vector quantity. You can get negative acceleration, but time is not going to be negative. If you get one answer, and the answer is negative, you probably made a mistake. But if you're solving a quadratic where one is positive and one is negative as an answer, you're just going to reject the negative answer and keep the positive answer.
I've seen like a couple problems they put like D1 is like -2 and 2 is like 4.
On a problem set in the textbook, I doubt it. I don't think they're ever going to write a negative time. But if you did see that moral, it's just the duration that matters, right? Delta t. So hypothetically, if you went from -2 seconds to 4 seconds, duration is just 6 seconds. So you replace delta t with 6. But the textbook you guys are using should not have a negative. At least I haven't seen a problem like that. Maybe like online as you're searching through problems, you might see authors writing that. But you're traditionally not going to see something that starts with a negative time. Okay? Now, theoretically, could it? Sure. Like, Maura, you could be at the starting line, right? And I could be next to you, and I could start 2 seconds early and get a head start. And you could say that I started at -2 seconds, you started at 0. Or I could say I started at 0, you started at 2 seconds later. Do you see the same how they're 6 and 1/2 dozen? So a negative over negative yields a positive. The value we're going to get for this is 5 or around 5, right? 5. 18 over 90. Yeah, 18 into 90 is 5. And what are my units for time here? Seconds. And if I don't know that, let's take a look at the unit analysis to show this. So let's do a quick unit analysis at the top. We've got meters per second divided by meters per second squared. That's what's happening right here, right? Everybody see it? Meters per second over meters per second squared. So what happens? I can show it mathematically so you can see it. But going forward, I'm just going to talk about this. Watch, ready? Instead of dividing by a fraction, we multiply by the reciprocal. Good, reciprocal or inverse, either word. So I can rewrite meters per second over meters per second squared as meters per second over second squared per meter and multiply them instead now. And what happens to meters? And what happens to one of my seconds? Yeah, they reduce, they cancel. Cancel, cancel, cancel with one of these, and I'm left with units of seconds. Now, it's really important that you pick up on the next thing I'm going to say, because it's going to save you a little bit of time in the long run. I don't want to have to do this every single time I have units, right? It doesn't make sense logically. So first, I know that if time is here, it's going to be seconds. So at least I know that. But let me show you something that most students seem to miss in math some point along the way. Look up here where I'm going to point real quick. Look at this equation right up here, right? Or this unit analysis. Meters cancel with meters. This seconds cancels with this seconds. And it becomes a unit of 1 over seconds. Does everybody see what results in black there? The top becomes 1. The denominator becomes 1 over second. And what's 1 over really? When you do 1 over in math class.
You multiply by seconds over.
Yeah, so it just becomes what in the end? It just becomes seconds. So whenever you have something that's in the denominator of the denominator, and that sounds weird, but it's what I'm saying, the denominator of the denominator really bumps up to the numerator. If that's not up here, write it down. Okay, a unit or a variable that's in the denominator of the denominator can bump up to the numerator. Because really you're just dividing by a reciprocal, which is multiplying by the inverse. You're dividing by a reciprocal, you're dividing by 1 over something, and then you multiply by the reciprocal itself. All right, let's continue. So the second part here is to talk about this concept of instantaneous again. Instantaneous. So it's the same thing as instantaneous velocity was. If you remember, instantaneous velocity was the velocity at an instant, not over a long time period. So again, we look at the same equation for acceleration, which is delta v over delta t. But if I'm looking at an instant in time, what does delta t become really? And we can see it in this problem. It becomes 0, because it's reducing. So if I wanted to know what my acceleration was from the beginning to the end, I might have a duration or a time period. But if I ask you, what's the acceleration at 2 seconds? Well, there's no way to use a formula for that. I mean, in calculus, you're worried about that, actually, I shouldn't say that. Right now, there's no way to use a formula for that. So we use this concept of what we called a limit last time. We look at the limit as we look at a time period that's getting smaller and smaller. Well, that idea, that concept that we're going to look at really, is really an easy way to see it graphically. So if we look at the next slide, we can take a look exactly here to see what we're talking about. So if we look at this graph, we can see that the velocity changes. How might you use your words and describe the motion of this particle based on this graph? And again, this is not position. Keep in mind, this is not position right here. So what might you say?
It gets faster.
It? What is it? Physics?
Particle.
The particle gets...
Sorry, the velocity
Good.
increases, and then between point A and point B, it keeps increasing, but at a more steady rate, and then it stays the same
At
B.
Okay, and then?
And then the velocity decreases when we go down to C.
Good. Now, I want someone to tell another story, but not using the word velocity and using the word acceleration.
The acceleration increases from the origin to end.
Velocity increases.
Or the velocity increases from the origin to
So what is the acceleration?
zero. Constant.
I know, this is a tough one. It's not constant necessarily here. The velocity one is easier one to say. Acceleration not as easy. Hold on, more a minute.
The acceleration is positive going up to A, and then it is less positive and then it becomes 0.
And then because it's a constant velocity up here, the acceleration is 0 at B.
And then it becomes negative acceleration as it goes down to C.
So what are we looking at here? Why was I using the pen? What are we looking at again? The what of the graph? Isabella? The slope. That's the word. The slope of the graph. The slope of the graph. So what we're going to notice again is that the slope of the velocity graph is really just acceleration. Huh? You hear Mr. Donishek? Can anyone hear that? And there's 0 acceleration. He literally was just talking about acceleration too. So yeah, we recognize that it's the slope that matters. The slope that matters. And think about that logically. It makes sense. Think about it. Go to point B. That's where it makes the most sense. At point B, isn't the velocity a constant? And when velocity is constant, what is your acceleration? 0. And what's the slope up here? So it just makes sense, especially in flat regions. Okay, now in the increasing region, it also makes sense, but you have to say the words. The velocity is increasing. Oh, what does increasing velocity mean? It means that positive acceleration. That's because the slope is positive. But then, as Mauro mentioned, look at the slope. It becomes less positive, less positive, less positive, 0. And then the slope becomes negative. And when it's negative slope, it means you have negative acceleration, and therefore your velocity is decreasing. So the concept here is very, very much like velocity with the position time graph. Remember, for position time, the slope was velocity. For velocity time, the slope is now acceleration. It's not that this is like a coincidence. There's a reason for this. We'll learn more about this year, but more really in calculus and in physics next year about the connection between these equations.
So that means from B to C, it's the acceleration is
increasing because the slope's negative, or what does that mean?
So you can't really say what the acceleration is doing unless you measure every single slope along the way, Jack. So right here, this acceleration is 0. Here it becomes negative. Then it becomes more negative, but then look, it becomes less negative. Then it's a pretty constant acceleration the whole way down. That hasn't changed. Then the acceleration becomes more negative. Then the acceleration becomes less negative. You follow what I'm doing? You see how I was shading?
Negative acceleration is just
A decreasing velocity in general. Now, we don't know if the acceleration is necessarily increasing or decreasing. We only know that based on the slope of the line to tell us more about the acceleration itself. But we can definitely say that, yes, in this region, acceleration is less than 0. In this region, acceleration is 0. And in this, I'll put little marks. And in this region, acceleration is greater than 0. We absolutely know those 3 facts. Okay? Until we really start to measure slopes at every moment, though, we can't really say much about the acceleration unless we visualize it. Positive acceleration, getting less positive, and then 0 on top. All right. Let's make another note here. Let's make another note. We talked about this with velocity. If the acceleration is constant the whole time, what can you say about the average and the instantaneous accelerations? They're the same. Let's write that down. If the acceleration is constant, then the instantaneous and average acceleration are the same. Again, if the acceleration is constant, then the instantaneous and the average accelerations are the same. And think about that logically. Draw yourself a graph if you need to. Like if I drew a graph of acceleration where acceleration were constant, this is what it would look like. Ready? There's my graph. That's acceleration being constant. Well, at any moment along the way, the instantaneous acceleration is just whatever the value is. Because again, this is an acceleration graph. So it's whatever this value is at any point. So we can call this 7 meters per second squared. So at any moment, the acceleration is 7 meters per second squared. And at any moment, for the entire duration, what's the average? 7 meters per second squared. So whenever you have a constant acceleration or a constant velocity, it tells you that the average and the instantaneous are going to be the same. That's a great multiple choice type question, especially for like a standardized test you might see. Yeah.
For a velocity graph that represents this, it would be a linear.
Correct. Very good.
For x would be exponential.
Nice. Very good. We're gonna get to that in a little bit. Very good, Valentina. So the velocity graph representing the motion she was just referring to at the bottom there would look like that, because constant acceleration of 7 means the slope of this graph is always going to be 7. Right? Think about that logically. When we had that on the first test, I gave you guys a velocity graph, right? And said which position function matches it. That's actually what you're doing there is calculus, believe it or not. Going from something like velocity up to position, or from acceleration up to velocity. And again, because this is a constant acceleration, it means that the slope must be constant the entire time. So I can tell you that that equation is definitely going to be 7 times t, and that's going to equal v. And I know that because, look, down here, the value of acceleration I listed was 7. So it means the slope of that function has to also be 7. Okay? Again, the slope of the velocity graph is the acceleration. Yeah?
So that means after 7 seconds, the object, whatever it is going 49 meters per second?
After 7 seconds have elapsed, it would be at 49, assuming it started at rest, yes, it would be at 49 meters per second. Because every second, it's gaining 7 meters per second.
Is there a limit to that? Or?
Well, technically speaking, yes. The speed of light is the limit.
Yeah.
And there's also a physical limit if an object is dropping due to air resistance called terminal velocity.
Right.
So we'll talk more about that. But theoretically, no, there's not. It will just continue to go up. But realistically, absolutely, there is a limit. Let's look at this table here. Let's take a look at this table together. And what I want to do with this table is just comment. Comment on the possible velocity initially and acceleration that would cause this type of motion. So, real quickly, tell me, what are some scenarios where you speed up? Like, how could you physically speed up? If blank and blank. I want you to fill in those blanks. You can speed up if blank and blank. Tell me about these two things. Christina.
You speed up if you are starting a race and you want to go faster at the end.
Okay, now use the words velocity and acceleration. Same question. Speed up if?
If you are starting a race at
accelerate at the end. Can somebody tag on to what she said? There's one other thing I want to say.
Accelerating positively.
Good. So it's the direction I want to talk about. So Christina's right. If you start with a velocity that's constant and you're accelerating toward the end, you're speeding up. But remember, it's a vector quantity. So when your velocity is positive initially and your acceleration is also positive, it means you must be speeding up. And that motion can be described and seen with this eraser. It's moving to the right, it's getting faster, it's getting faster, it's getting faster, because it's accelerating positively. Now, first of all, how many in the room run at some point, cross country, track, right? Okay. Or we've run for exercise at least at some point in our life. We've all run, man. So when you're running,
Never gonna go fast
I've never run in my life.
I only skipped.
So when you're running, what do you feel against you when you run? What do you physically feel? Air, right? Air resistance. So while you're running, you're always experiencing what kind of acceleration while you're running? You're always experiencing negative acceleration. Now, what if I'm running left though, Mauro? If I'm running with left velocity, then what kind of acceleration am I feeling actually? So that idea is kind of weird, right, to think about. So let's discuss this idea for a second again. If I'm running and something's slowing me down, I know that the wind is opposing my motion. Opposing. So we use the phrase deceleration in physics to mean that something is simply slowing down. So we're going to get to the second case in the first one still. But looking at the second category here, when we see slowing down, let's jot down the word decelerating. And decelerating is a word that is thrown around too liberally. It's like thrown around too much in certain circumstances, but it's not true. So, just because you have negative acceleration does not mean you're decelerating. It just means deceleration that you are at opposing values. So if I'm running this way and the wind is pushing back, that's deceleration. But if I'm running this way and the wind is pushing back, that's also deceleration. So deceleration is not about the sign of acceleration being negative or positive. It's about your motion slowing down. So the first case was negative, negative. Why does this second case I'm going to write for the first one make sense? For speeding up. How come negative, negative after positive, positive for speeding up works? Why do you still speed up, Jack? What do you think?
Two negatives makes a positive.
Okay. It's a good way to think about it. And that's a good way to remember it, by the way. That's actually a really good way to remember it. Two negatives make a positive, being positive, speeding up. That works. Okay. But physically, yes.
Speed isn't a vector quantity, so speed can only be positive. So the more negative your velocity is, the more positive your speed is. So if your acceleration is making it more negative, making your velocity more negative, then you're technically speeding up.
But in what direction, Mauro? In the negative direction. Do you hear what he's getting at there? The speed has to do with your actual motion, not the direction. So if I start with negative velocity, but then acceleration pushes me forward with more negative acceleration, making it faster and faster and faster, or my velocity more and more and more negative, I'm getting faster, just in the negative direction at that moment. So as Jack said, you could think two negatives or two positives make a positive, right? Either direction there. Now what about slowing down? As a result of what Jack said, what do you think is going to happen with slowing down here? What is your guess or what is your idea? Janice, go ahead.
It would be a positive and negative.
Good. Or?
Negative and positive.
Very good. So either of those scenarios involve deceleration. And that's what we just mentioned. If I'm moving right, but the wind is pushing me back, I'm decelerating. If I'm moving left, but the wind is pushing me right, I'm also decelerating. So deceleration simply means that your velocity and your acceleration have opposite signs. They disagree. It's like a tug of war. Okay? It'd be like me pushing a couch across the room, and then you're waiting here and just be a jerk and you like push back against me, right? It's slowing you down. You would be negative acceleration, I would be positive velocity, we would battle. And as a result, it would slow down. The motion would slow down. Okay, so that's what deceleration is. Really important that you understand that word, deceleration. Because you're going to see it on quizzes, on tests, on problems, and you need to know that if you see the word deceleration, it doesn't mean that your acceleration is negative. It just means it's opposite your velocity. So if my velocity is negative and I'm decelerating, my acceleration is actually positive. Again, they oppose each other while decelerating. How about this last couple here? How can you have constant velocity? How is that possible? How is that possible? You can think of this from last. Yeah, Juliet.
If you have could you have a positive or negative initial velocity, but then no acceleration?
Very good, Juliet. Okay, 0, and I'll write the word 0 actually, because look at a circle now. When you have 0 acceleration, it doesn't matter what your initial velocity is, it will be constant. Very good. Second one. How about after that? Speeding up from rest.
0 and then any velocity and any acceleration.
Very good. Positive or negative again there. Very good. And again, I'm not moving. And if I get positive acceleration, I go this way. If I get negative acceleration, I get pushed this way. But either way, I'm speeding up from rest. And then the last one. Yeah, very good. I saw everybody go like this. 0, 0. Yep. You have no initial velocity, and you are not moving only when you have both equal to 0. This table is really, really useful. Okay, keep that in the back of your mind. Keep this idea in the back of your mind. And the way I organized it, I did on purpose so that you have the concepts tiered together, or tied together here between the two. Okay. Continue. All right, so let's look at one more example of a theoretical one, and then we're going to get into some heavy math after this. And the heavy math we're going to get into, I know we have so much time. The heavy math we're going to get into is a derivation, it's called. And I'm only doing this in an honors course. I don't really do this in a regular physics course. A derivation is going to show you in a minute where equations come from. Okay, we're going to come up with 3 new equations as a result. So let's start with this problem first, and we'll get into that little bit of heavy math. So we look at the problem. It says, if the velocity of an object is 0, does it mean the acceleration is 0 automatically? If the velocity of an object is 0, does it mean the acceleration is 0? If the acceleration is 0, does it mean that the velocity is 0? So let's just talk this through. Based on our last table, it would help for sure, but let's talk it through. So how about the first one? If the velocity is 0, does it mean that the acceleration has to be 0? What do you think, George?
Yes, because if there's no velocity, there's no speed. Wait, no, not necessarily. But if the velocity is 0, there's no way it could be moving. So.
What do you mean?
If the velocity is 0, and let's say that if the velocity of an object is 0, that means that it can't move. So if it can't move, then the acceleration has to be 0 as well.
I get the argument.
And wait, no, unless you go back to your starting point.
Okay, so that's the case that is not true, right?
Yeah.
So George was thinking for most cases, oh, this is true, or if you have 0 velocity, you can't have acceleration. But then he came up with one case, it seemed. Can you explain that case a little more?
Well, if you go back to your starting point, that means you did have some speed, and that means you could have some acceleration, but your velocity is still going to be 0. So your acceleration could be positive.
Okay, now remember, for this problem, it's not saying average velocity over the whole period. So if you look at the wording of it, if the velocity is 0, does it mean the acceleration is 0? They're really referring, it's right out of your textbook, it's really referring to instantaneous velocity and acceleration. So is there a possibility that there's an instant where your acceleration is positive or negative or some number, yet the velocity is 0? Can we think of a scenario like that? Because I can think of a scenario, actually. I like your logic, George. Your logic made sense, but then you thought of the one possibility you talked about returning to your spot. That's a good example to think about, but I need more than that. What do you think?
No.
No? Anybody think of something? It's not easy to think of a case like this. Yeah?
I could try. If you were accelerating, but you were going if you had a negative velocity initially,
Negative velocity, let's do this, okay?
and then you're accelerating, and then
Which your acceleration, positive or negative?
positive,
Okay, so it wins against me.
and then you pass 0, so your velocity becomes 0, but you're still accelerating now.
And then what would happen after it's 0?
Eventually come back this way.
Let's talk about that for a second. That's right, very good, Laura. That's very good. It's the turning point is the problem here. The turning point. That's when you said turn around, go back to your spot. So what happens, the easy way to think about it, I'm going to explain it a little bit simpler. Think about a trampoline. You've been on a trampoline at some point, right? Or you know what a trampoline is like. Okay. You're jumping on a trampoline, right? When you jump on that trampoline and the trampoline gets stretched all the way down, what happens at the very bottom of your body for a moment? You stop for a moment, don't you? you're moving down, which is negatively, and then you stop for an instant in time. And then you start to move upward, don't you? Well, your velocity went from being negative to being positive. So your velocity changed, didn't it? And the definition of acceleration is a change in. So when you are jumping on a trampoline, the trampoline springs are accelerating you upward. So the whole way down, here's your body, hits the trampoline, the springs stretch, the springs are pushing back against you. This is called Hooke's law, we'll learn about later this year. Hooke's law causes a push back in the direction, which will cause you to get launched upward. So the entire time on the way down, when you hit the trampoline is pushing back up with acceleration that's positive. So your velocity is negative, 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 negative. You stop, and then your velocity is positive, 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 and then it launches off. And then we didn't talk about gravity yet. We're going to get to that soon. But what does gravity do? Which way does gravity pull you? Down. So the whole way up, which way is gravity accelerating you now? It's accelerating you down. And then what happens at the top? What do you do again? And then you turn around, don't you? So at the top and at the bottom, what's your velocity at both those moments? Yet you have acceleration at both those times. Because again, gravity is always pulling you down. Whether you're moving or not, it's still accelerating you. And the spring in the trampoline is always pushing you up when you're in contact with it. So it's the same problem as what Morrow said, except it's just different when it's left to right. So if I'm moving leftward, but I've got, like, say, a thruster off a car. So here's the car, all right? Here's like a rocket booster on the back of the car. So, here's actually, what I think about would be like, like reverse thrusters on like the SpaceX. Anybody follow Elon Musk and the SpaceX stuff he does with the landing rockets? So those self-landing rockets have reverse thrusters that fire in all directions to keep it stable as it lands. Your velocity is downward, yet your acceleration, your velocity is downward, and you're pushing like that into the ground, which accelerates you upward, which is what causes the rocket to coast. So this is what you're seeing visually. This is the thruster. As the object is moving, the thruster is pushing that way, so therefore it's pushing you back, and then eventually the thruster causes you to stop, and then if it kept thrusting that way, it would push you forward. So eventually you're going to stop and then turn around. The moment that you stop is when your velocity is zero, yet you do have acceleration still, that instant in time. Now how about the second one? The second one is a little bit easier, I think. The acceleration is zero doesn't mean the velocity is zero automatically. If the acceleration is zero, does it mean that your velocity is zero automatically? What can you say about this? I'm seeing the same hands. I'm not ignoring you guys, I promise. I just want to get other people interested. If your velocity or your acceleration is zero, does it mean that the velocity is necessarily zero? What do you think, Justin?
No, velocity is constant.
Good. The velocity could be constant. Yeah, it could be zero, right? Because zero is a constant. But the velocity could still be a value of 5 meters per second, feet per second, miles per hour, whatever it may be. Yet the acceleration is zero if that velocity doesn't change. So the second answer is, if the acceleration is zero, does it mean velocity is zero? No. Again, because the velocity could be constant. These are two questions that are asked on like every subject test, every AP exam, the concept behind this. Now, it might not be directly asked in these exact words, but the idea of differing acceleration and velocity comes up over and over and over again. So I'm introducing it to you here, but in your homework you'll see I asked you other questions that involve this idea again, and then I can guarantee you on your test you'll have something that involves this kind of a concept, where if they have one is zero, does the other one have to be zero automatically? All right, let's start this derivation that we're going to get into for a little bit. So this, I say heavy math, by the way, only because we're going to be doing a lot of math with all equations and not numbers. So it might seem heavy because it's going to be all variables and seem like, wow, there's so much going on. But how many people, show of hands, how many people feel confident in substitution principle or substitution method? I hope everybody, okay. It's all right, if not. What I mean by substitution is substituting one equation into another. That's all this is going to be. So if you feel like you're getting lost along the way, stop, pause yourself, and say, what am I doing? I'm simply substituting one equation into another. That's all we're going to be doing. But we're going to do it several times over and move some stuff around algebraically, so it may seem a little bit tough at first. So, to get our first equation, we're going to start, and the first one is very simple, real simple. Start with the definition of acceleration. The definition of acceleration is delta v over delta t. So this becomes simply v minus v0 over t minus t0. Now, for all of these equations that we're going to look at now, we're going to make the assumption that t0 is 0. So let's jot that down at the top. Oops. Let t0 equals 0. And simply put, let all the problems start at time equals 0, meaning at the beginning. So what this does to this equation is it makes it simplified a bit. V minus V0 over t. Now, the first equation that we're going to really care about is this one right here, but solve this for V. Just solving this for V. Multiply by t, add the V over. Again, multiply by t, add the V over. I'm going to solve this for V. So again, this is going to become AT equals V minus V0, or V equals V0 plus AT. And that's our first of the three main equations. V0 plus AT. Anybody see any sort of interesting nature about this equation if they look at it? I know it's weird, and I don't know how I can say this right. Anybody see anything about functions when they look at this equation is what I should say. Functions. What are you seeing, Christina?
It reminds me of the y equals mx plus b.
Y equals m, slope is acceleration, x plus b. What was b in all math problems? B was the starting value, y-intercept. Well look, starting velocity. Hey, what did we say acceleration? Acceleration is the slope of the velocity graph. And look, the acceleration is right in the spot where slope would be. This is m. X, which is normally your x-axis. What do we call the x-axis in this class? Time. That's t. So this is really analogous. This is analogous, maybe jot it down below, to y equals mx plus b, or b plus mx. I'm putting it in a direct order. So your v0 is your starting value, your acceleration is your slope, your time is now your independent variable, and your dependent variable along the y-axis is your current velocity. So this equation is extremely useful, and we're going to see how it behaves as a linear function, really. Behaves as a linear function. What would that look like graphically? Just so we can see it, I'm going to put that below. Graphically, I would just illustrate that as follows. Okay, that's how I would illustrate that graphically. The y-axis is v, right, which is here. That's y. The x-axis is time. The slope is acceleration. We said the change in y, the change in x is acceleration. And the starting value, or the y-intercept, is your initial velocity. That's what that would look like graphically when I think about that equation. Now, whether you realize it or not, you guys already did this in the lab the other day. Remember the lab the other day? The velocity graph just looked like that the whole time when you push the push cart up? So you're going to start thinking about this. And why did the velocity have a negative slope? Because when you push the cart up, what was it accelerating? In the negative direction, or deceleration. So it was slowing down the whole way up. So as a result, this object eventually came to rest in the lab. Here, we're just seeing the positive incline. Maybe it comes back down, or maybe the velocity gets lower. But that's the general shape of that one. Now, for the second equation we want to look into, let's start off with this idea of the definition of velocity from chapter 2. And that definition, actually, I'm going to put it over here. The definition of velocity from chapter 2 was v bar equal delta x over delta t. Remember, that was the definition of velocity from chapter 2. And we were told in this part that we could say, all right, well, v bar is really x minus x0 over t minus t0. Well, again, t0 drops off because we say that t0 is simply 0. So that's the equation I have. And you might for a minute be like, this isn't helping me at all. But I know this right. You did this last chapter. You can multiply by t, add the x0 over, and you get x by itself and the position function. We can do that like we did in the last chapter. But what we're actually going to do is we're going to do a little bit more than that. So let's first solve this for x like we're saying. So we'll multiply by t on both sides. And then move the x0 over by adding it. And again, this is nothing new. We saw this equation last chapter. for those of you, remember for the Arthur-Betty problem, this was the equation you really wanted to use in the Arthur-Betty problem. Position equals initial position plus velocity times time. Now, for this equation, though, there's something unique we can do. We can actually recognize that in this problem, we are looking at, it's italicized, constant acceleration. And when acceleration is constant, I can look at this graph, take a look at this graph down here, and I can recognize that, well, what's the average velocity going to be in this problem? If it's constantly accelerating, the average velocity is right in the middle. It's smack dab in the middle, right there. Again, if it's constantly accelerating, the average velocity will be this number right here, which is really just the average of these two values. Give me one more second. So you can do this. You can rewrite this as average velocity and take this equation and substitute it right in there for V bar. We're going to pick up with this tomorrow. Listen, your homework at the end is far more extensive than what you can do tonight. But there are a lot of problems that are theoretical in the beginning. You can do those ones already if you'd like to. Okay, so I'm going to see you guys again on Thursday. We're going to finish this lesson. We're going to do a lot of math problems, and your homework has a lot of math problems. But, again, any of the homework problems that don't involve math, if you want to get a head start in the next few days, you can do so. Okay? Have a good day, guys. Good job today. It was a lot of work. I appreciate it. Focus. What we did last time was we ended first with this idea that we have this velocity formula which looks very much like a linear equation, mx plus b. And then we started by looking at a new formula, or an older formula, that we were going to make into a new formula by using this idea. And this is where we stopped. Last class I said to you, we could solve the velocity equation where there's no acceleration at all, but then we can recognize here that if the acceleration in a problem were constant, the velocity in general would be the average of the two positions, the initial and the final, assuming acceleration were constant. So we're going to take this expression and plug it in here for V bar. So let's continue that idea. So this looks like the following. When plugged in for V bar, I'm going to continue up over here. This becomes x0 plus. Now instead of V bar, I'm going to put that entire expression there. X plus x0 over 2. Let me move the screen over a little, sorry. And then I'm going to put the t next to it still. And that's going to equal the overall x right here. Okay, and I think actually last class... Sorry, when I wrote this down last class, nobody, feel free to correct me. Sometimes that could seem a bit intimidating because I go through things quickly. So if you ever see a mistake in something, feel free to correct me. Does anyone see the mistake from last class that we ended last class on? That I just kind of overlooked? Nobody picked up on it? Okay, I'm realizing it now as I go through this. This should state V plus V0, not X plus X0. Because as I'm doing this in my mind, I'm like, oh, that derivation isn't going to be right. If you notice stuff, if you ever notice that like something doesn't seem right, or you're like, oh, why did I get something different than Mr. Howe? Feel free to point it out. That should have said V plus V0. Because what we're doing is we're saying the average velocity is the average of the initial and final velocity, assuming that we're increasing our rate at a constant rate. So that's like, again, a person stationary and then moving across the room, gradually getting faster and faster and faster. And the reason I picked up on that is because I know what the formula eventually should become. And I saw there was an x here. I'm like, wait, there's no x here, and there's no x0 in this problem. And it was v plus v0. Now, at this point, what we can do is we can distribute that time t. We could recognize here, well, that time t gets multiplied. So this becomes x0 plus v0 times t in the numerator all over 2 equals x. And I'm writing it that way for a reason. What we're going to notice here is that we're going to be able to substitute in. And we could substitute in because if we look at the equation from earlier, we'll recognize that we can utilize this right here. And the spot we can utilize this is by taking this first equation and plugging it in for v right there. So let's take the expression v0 plus at for v and place it right here in that equation. As a result, let's take a look at what we're going to get. We're going to get here v0 plus at plus v0 times t all over 2. Okay, so again, what am I doing? I'm taking, and I'll use yellow so you can see it a little bit clearer. I'm using this one and plugging it in right there for v. Okay, I'm taking this expression that we saw, which is, we called it our first kinematic equation. We're taking our first kinematic equation, plugging in here for v to yield this. And the reason we do that is because now this simplifies. And what we recognize is that now, if I have a problem that does not involve final velocity, I can use this equation. Because there's no final velocity anywhere in this equation. Whereas earlier, to use this equation, I have to have something about the final velocity. But let's say a problem didn't give us any information about final velocity and didn't give us any information or ask us to find the final velocity. This equation becomes much more useful to use than this one does. So once we get to all three equations, we're going to list them and talk about them more, about why we're going to use certain equations in certain circumstances. But that's the reason we plug in for v, to get rid of final velocity, so that everything is in terms of initial velocity, acceleration, initial position, and time. The key is to eliminate variables, which is what we're doing. We're using substitution method by plugging in here and thus eliminating v from the equation altogether. So this one, if we simplify things a little bit, okay, all we want to do is simplify things a bit. We're going to end up with x0 plus. Now we're going to have two v0s here, right? So 2v0 plus at times t all over 2. And then I can distribute that t to the entire thing. When I distribute that t, I'm going to take and distribute it here, right? And here. I'll recognize that this equation becomes x0 plus 2v0t plus at squared all over 2 equals x. And then the last step for this equation, before we get the one that we use a lot, is going to be to divide by 2. 2v0t over 2 becomes v0t. And then at squared over 2 is 1/2 at squared. And this is equation number 2 that we want to make sure to box in or circle, whatever we do. So first equation, second equation here. And what I want to point out are a couple things about this equation if we look at it carefully. First, if the object started at what we're calling the origin, this doesn't matter, right? No x0. Let's start writing these notes down below the equation. If it starts at what we call the origin, or we're calling the initial position 0, this drops off. If it starts from rest, this whole term drops off. When I say drops off, I don't mean it just magically goes away, but if I start from rest, what does it mean about my initial velocity?
0.
And therefore 0 times t is clearly 0. So you want to write down notes that, again, when you don't have initial velocity, this part of the equation is not involved. When you don't have an initial position, meaning it's 0, this part is not involved. Hypothetically, take a look, please. What if acceleration weren't involved? What part would drop off then?
The third part.
And what do you get? Everybody take a look up. This is the position function from last chapter. Remember Betty and Arthur? X equals Arthur's starting spot plus Arthur's velocity times time. Or Betty equals Betty's starting position plus her velocity times time. So without acceleration, this equation goes back to the position function from chapter 2. Chapter 2, am I right with the numbers? Yeah, chapter 2. The textbooks are great being honest numbers. So from the one-dimensional constant motion problem is this. Now that we have acceleration, we're just adding on this last term. Okay, just adding on that last term. So going forward this year, if you're given a problem that does not involve acceleration, you could use v bar equals x over t, or delta x over delta t that we used before, that first equation all the way up here. You could use it. But if acceleration is 0, you could also just do this. Okay? You could literally cover this up and say, well, if acceleration is 0, my initial velocity isn't changing, right? So what does this become? It becomes a constant, which is right here, constant. Okay? So again, when your acceleration is 0, just use this formula. It makes a lot more sense than going back to the beginning of the year and having to remember that formula, because this is on your formula sheet. So just drop it off, and initial becomes a constant. Do we get why this becomes constant velocity in this circumstance? What is constant velocity defined by? What is constant velocity defined by?
Velocities with no acceleration.
Yeah, with no acceleration. So if I set acceleration as 0, it means that my initial velocity can never change. So although we're calling this initial velocity in this formula, if acceleration is 0, this inherently becomes constant velocity or average velocity. Again, when acceleration is 0, this becomes that. This is stuff that you should be writing down, not just listening. So if it were me and I were a student, I'd be writing, oh, look, x equals x0 plus v bar t, and I would write myself a note that this occurs when acceleration equals 0. That's what the equation reduces to when acceleration is 0. When initial position is 0, it results in that equation right there. When initial velocity is 0, it results in that equation. Are you going to memorize these? No, you're not. It doesn't make sense to memorize every possible case. But you need to be able to manipulate this governing formula. Put like asterisks next to this if you have to. This is probably the most important formula. Remember I said this chapter is going to govern all of our work for the rest of physics and AP physics? The equations we use. This one is by far the most important of all of them. Okay? It's by far the most important. This one is important, but it's pretty easy to get this equation from just having the definition of acceleration. That was a quick, easy one. This one is the most important by far. Now, the third of the three equations comes from combining stuff that we have up here already. Okay, it comes from combining a lot of stuff up here. I'm running out of room and it's going to get so small you can't see, so I'm going to add a new page in here. Okay, I'm going to add a new page. So jot down anything you need to jot down before I start on a new page here. So the third formula we're going to look into is the following. We start this third formula. First, we'll start with our, let's see, I want to do that one first. Yeah. Let's start with our definition of position with no acceleration. Again, with no acceleration. Remember, what am I really doing? I'm doing this, right? And then I'm saying, that's gone, no acceleration. And again, normally V bar is V0, but because of no acceleration, I can say that V0 is an average or a constant the entire time. Then what we're going to do is, we're going to take the definition of average velocity that we wrote down last time. And we can use this, remember, when acceleration is 0, we're allowed to write that. It's just the average of the two. And we're going to take that and substitute it in right there. And we're going to write the following. X equals x0 plus that entire expression times time. What we're going to then do is we're going to go back to the first equation we derived. So if you need to go back a slide or scroll up a little bit, look at that first equation we derived together and solve it for t. Again, take a look at the first equation we derived and solve it for t. And that first equation that we derived, I'll put it on the side so you can see what we're doing, was this one. All right, that was the first equation we derived. And we're going to solve this for t. So let's subtract v0. And then let's divide by a. And we're going to take this expression right here and plug it in for time. Okay, we're going to take that whole expression there and plug it in for time. And what's cool about this derivation, this last one, is you finally see applications of things you're learning. Well, not finally, but you see applications of things like factoring and difference of squares. They play a role here finally. Okay, you learn that in Algebra 2 a lot, but you don't ever see it really in application until you get to physics. This is one of the first times you're going to see difference of squares play a role. It will come up many other times in this course. Okay, difference of squares, if you recall that factoring technique. So this equation becomes then x equals x0 plus, and this is v plus v0 over 2. And then when I replace the next part, it's v minus v0 over a. When I look at the numerator now, if I were to multiply out that numerator, I could see that the middle terms are going to cancel. If you were to FOIL out the numerator, this is like x plus 3, x minus 3. Does everybody remember difference of two squares? You got to remember that. If you're not sure what I'm saying right now, take a look in your math book when you get home tonight, okay? Difference of two squares, x plus 3, x minus 3. That easily becomes x squared minus 9. So the result of this is just going to be v squared minus v0 squared. I know that already. Now, if I didn't know that, I could just FOIL it out and prove it. Okay, so I'll show it to you in case people are a little bit lost with the difference of two squares part. So you see what's happening. This becomes, again, x equals x0 plus. Now the denominator is just 2a. That's easy math, right? Multiplying fractions, multiply the denominators. The numerator, when FOILed out, again, becomes v squared plus v0 minus v0 minus v0 squared. That's what this equation ends up looking like when you FOIL out the numerator. But look at your little terms. What happens to them, obviously? They reduce. They cancel each other out. So we end up with an equation. That does not, in this case, involve time. And this is not the way the equation is actually expressed. This can be the way it's expressed if we wanted to. We could say x equals x0 plus this whole thing. But your formula sheet solves this equation for v squared. Can you practice doing that on your own? Solve this whole equation for v squared. Think about what has to move first. God bless you. Think about what variable needs to move first. And I'll give you a hint. It's the simplest variable involved that needs to move first. I'm going to do it a little bit delayed from what you guys should be, so I'll give you a second to start doing it, and then you can look up as I'm doing it. Yeah. So that's the first step you should take, right? Move over the x0. If you didn't know that, if you didn't think that, instantly, you got to ask yourself this question. What is x0? It's a position. It's a number. It's a constant, right? It's some value. So if I had a number right here, how would I solve this equation? I would subtract that number first. If everything were numbers except for the thing we're looking for, which is v, we're only looking to solve for v. Imagine everything else are numbers. You would start by moving this number over. Then you would start by thinking of this as a number. You would multiply by this number. You would then add this number. So whenever you're having trouble solving generically, treat everything as numbers in your mind except for the one thing that you're solving for. And in this case, v is what we're solving for. Okay? Actually, it's v squared is what they leave it as, but that's just a traditional formula. So we're going to go ahead and move 2a over. And then we're going to add v0 squared over. And notice the symbol I'm using there? I could use that. Why not, right? What does delta mean again? Delta, change. So as a result, I see x minus x0 here. That's the change in position. That's all it is. The final position minus the initial. So this is my formula, or my third of the three big formulas. Again, write yourself a note. What is not needed when using this formula? What variable? Time. Very good, Jack. Time is not necessary. So, when it comes to problems with accelerated motion, we're about to start. In about 30 seconds, we're going to start some heavy math problems. You need to ask yourself, what are your givens? What are you looking for? Which of these three equations now there's not one equation, there are three choices. Which of these three equations involves what you're given and what you're looking for? So if the problem doesn't involve time and doesn't ask you for time, you're going to probably use this formula, right? If the problem involves time, it will most likely be one of the other two formulas. Have we picked up on this now? Is it clear what I'm saying? You need to be able to navigate your formulas and think about which one is useful at which circumstance.
So you said the second equation
Does not involve final velocity.
Okay.
Okay? Take a look at it. It's missing v, right?
Yeah.
It's got v0, it's got t, it's got a, it's got x, it's got x0. Okay? The first equation does not involve position. Go back to the first equation, v equals v0 plus at. That equation is useful when nothing about position is given. The second equation is useful when nothing about final velocity is given. And finally, the third equation is useful when time. And when I say it's not given, I mean it's not given nor asked for. If the problem asks you for time, you absolutely can't use this formula to solve for time because it's not there. Okay, so it's just logical at that point. Let's jump into some examples of this, just so you guys can kind of see this a bit better. Now, on the slide, I'm going to point out, this is what I've been saying to you all along. This is literally what I've been saying, right? Reread the problem. Decide, in this case, the object and the time interval. Draw a diagram. That's something I've been telling you guys. Write down what you know, what's given. Try to go think about the principles of physics to help you. That's useful, but I personally consider the equations next. And then I go through the rest of the problem, carrying out calculation, making sure it's reasonable, making sure I have units. So for those that have been like, I want a step-by-step guide for these problems, this is it. Right out of your textbook. I didn't quote John or give credit to John Coley up there. It's not my writing here. This is right out of your textbook. It's an image in there at the very end of chapter 2. Okay, so we're going to take this structure and apply it to every problem going forward. Okay, every problem going forward. So let's look at example 3. We'll do this one together first so we can actually go through it. As I go through it, I'm going to underline what's important. A race car reaches a speed of 42. Right away. Reaches a speed of 42 meters per second is important for sure. I'm given values. I'm told it reaches that value. So maybe it's accelerating up to that value. I don't know yet, but maybe it is. It then says it begins a uniform negative acceleration using a parachute. Ever seen parachutes deployed on cars or rockets to slow them down? And a braking system that it has, and it will need 5.5 seconds to come to rest. There's a lot of info there, right? So let's go one step at a time here. It then begins a uniform negative acceleration. That's huge, because that's the beginning of our problem now. So it turns out that although this race car reached a speed of 42, nothing mattered before it got to 42. It then began to brake. It then began to have negative acceleration. So prior to getting up to 42, we know nothing about this problem. I don't know if the race car driver accelerated for 20 minutes to get up to 42, or maybe 10 minutes, or maybe 3 seconds, and he's in a Ferrari. I don't know anything about it. I don't care. Because the problem, as I continue to read, is concerning the accelerated motion after the brakes or the parachute has been deployed. Okay, so that's a key point there. Let's see. It says it will need 5.5 seconds to come to rest. Obviously, that's going to be useful. Okay, that's going to be useful. Come to rest is also useful as a separate entity. So I'm going to line both of those in 2 separate colors there. I'm trying to color code so you can see later what I'm getting from what. If a boundary exists and was 100 meters ahead of the car's position when it started braking, will it stop in time? The problem is not directly asking you anything. You have to figure out what it's asking you here. It's not saying, what's the final velocity? What's the time it takes? What's the position? That kind of a question will be a non-honors course, to be completely honest with you. It would say, find the time it takes to do this. This doesn't tell you what you're finding. Can anybody tell me inherently, though, what you are actually finding here? Seth? Yeah, Seth?
Oh, so it's finding, when it starts braking, when it comes to a stop at 100 meters,
So what are you really finding, Seth?
the final position.
Very good. That's it. The final position. Some people might say the distance the car brakes for. That's fine, because we're going in one dimension, in a straight line. So the final position will really just be the distance you brake for. That's fine. You can use it. But final position is the key phrase there. So although it's not clearly indicated, it says, will it stop in time? This is where the diagram really plays a role. Here's the car initially. The car starts to speed up. It gets up to 42 meters per second. I'm going to call that my initial, because that's when the problem starts. That's when this driver hits the brakes. That's when the driver physically stops the motion. Again, this car is moving up until there, but this is the beginning time. Beginning to ends?
I can never
Thank you.
spell it right.
It looks weird, that's why. Okay, that's the beginning of the problem. The end of the problem is when it stops. But does it stop before the wall or after the wall, right? That's the question. So, we draw a wall first. A boundary is traditionally drawn with lines to the side of it that are like angled to show that there's nothing beyond that. It's a ceiling, a wall. You'll see that a lot in textbooks. Okay? So there's your boundary. So really, we know that this car is going to continue along this path, but is it going to end up here? Is it going to end up here? Will it hit the wall and end up here? That is our question. We don't know where this object will end up. Therefore, we are looking for the final position. The position at the point 5.5 seconds after it actually starts braking. Okay? We know it's 5.5 seconds. That's given at least. So either at this moment 5.5 seconds have elapsed, or maybe here, or maybe 5.5 seconds don't elapse until we get to here, and therefore we hit the wall before it stops. So the time is a strict factor. It's a constraint here. Yet the displacement, the final position from the initial position, is what we are trying to figure out. Okay, so our goal is to say, well, x0 is just 0. Let's call that the starting point. And our goal is to figure out, what is x in this problem? Where is it along its trajectory? It's not maybe the right word, or its path. Its path taken. Okay, and what else do we know? We know at this moment, the time, God bless you, is going to be 5.5 seconds. And the initial time is going to be 0 seconds. Why am I doing that? I'm doing that again to simplify things. Don't call t0 1 second just to be annoying, just to be like that person. Trust me, it won't help you in the long run. When a problem gives you a duration of time, call the starting time 0. It just makes sense. It makes the problem easier. Whenever you have anything equal to 0, those variables drop off in the equation. Now, I have to ask myself a question next. What equation do I have that involve x? How many do I have that involve x? Take a look at the last 3 equations. 2 of them, right, involve x. Now, in both of those equations that involve x, what other variable do they involve that we do not have? What is it, Justin? Acceleration. X equals x0 plus v0t plus 1/2 at squared. V squared equals VO squared plus 2a delta x. Both of them involve a. Therefore, we can't actually do this problem yet. What do we need? So, can we think of another formula that we can figure out the acceleration from that may not involve position? Because we don't know position, right? So I can't use either of those 2 position formulas we just talked about because I don't know position. And I don't know acceleration.
Acceleration equals the distance, the change in velocity over the
Yeah. You could go with either the first of the big 3 formulas we're talking about, or go back and say, hey, acceleration by definition is this. Absolutely, Caroline. I would use this one here. Even though this is one of the big 3 formulas that I talked about, if I rearrange it, I get back to this. Remember, this is where it came from. Substitute in v minus v0. That's where these come from. T minus t0 when t0 is 0. So I could use either equation here. You can pick to choose which one you want to use. I would choose this one, even though it's not on the formula sheet, because I remember the definition of acceleration is a change in velocity over time. And because I'm trying to find the acceleration to then use it in my position equation, I wouldn't want to have to resolve this for a. You follow what I'm saying there? Would I want to resolve something and do more work? No. I'd rather use the formula that already has a already solved for directly. So let's take a look. My change in velocity, it starts the car at a velocity of 42, but eventually it comes to rest. So what's the velocity at the end? Okay, so we know that already over here is 0. So final velocity minus initial velocity all over the time period. So my acceleration in this problem is absolutely necessary to evaluate prior to seeing what the position function is. Now, I could also, if I wanted to be fancy, I could just take this definition of acceleration and plug it directly into the formula for position wherever acceleration occurs. Think about that for a second, right? Think about that for a second. If I wanted to use this equation later on, so in a moment we're going to use this equation right here. But if I look at this equation, I could simply take delta v over delta t and replace a with it. It's algebraic substitution. I don't have to get a number for this. Sure, I can get a number. What do I get? What's negative 42 over 5.5 give us?
Negative 7.63 repeating.
So negative 7.63 repeating is going to go in here, right, for acceleration? But if I wanted to make the answer more powerful, I could literally just substitute this expression in here and put delta V over delta T there, and then plug in numbers at the last step. And right now you're like, oh, that doesn't make any sense. Trust me, it will. Later on, you're going to want all your answers in variables, and if you go on to AP Physics next year, the exam is mainly in variables, not in numbers. So you need to get used to using variables and solving equations all in variables. For the sake of this course right now, you can do it either way. So because this is one of our earlier problems, I'm going to plug in numbers so it's more reasonable for you to see. So my position is going to be my initial position, 0, plus my initial velocity, oops, I should put units, my initial velocity times the time period, plus 1/2, negative 7.63, you said? 63, Eduardo?
Yeah, it's 6 weeks.
Thank you. Acceleration times t squared. So what I'm doing is I'm evaluating this right here and plugging it in right over here for A. So you're going to find that with physics, there might be roadblocks along the way. If you stop at the roadblock and give up, you will never do well in a course like this. You need to find the way around that roadblock. And the way around it in this problem is this formula right here. Because if you try to find x, you can't do it without acceleration. So you've got to get your acceleration first, either as a number or as an expression, and plug it into A, either as a number or as an expression. Okay? And I'll get a value from this quantity. I'm going to get 115.5. Check my math, check your math, please. Okay, it should be right. I work out these numbers ahead of time sometimes, so that one I definitely did. What does that tell me about the problem? Because that is not my answer. The problem never said, what is the displacement after 5.5 seconds? That is not the question. What was the question, Turner? Jack Turner? Sorry. I'm just using last names, you two. It's easier. You have both hands up.
If a battery exists and it was 100 meters out of the current position and it was breaking, will it stop in time?
It will what?
Will it stop in time?
So what is the answer to that? No, it will not stop in time. Because how long will it take to stop? 115.5 meters. But how much distance do you have? Only 100 meters. So you will definitely hit the boundary or hit the wall. The wall, again, was 100 meters away. That's something that I didn't put in my diagram, so maybe I should add that to the diagram. Right? I know for a fact that this is 100 meters across. Okay, it is 100 meters across. So it's really important that we recognize, although a problem doesn't ask us directly for something like position, we're still solving for it to answer the question that's being asked. For example, let me give you a follow-up. Ready? If the problem were to say, a different problem, but if a problem were to say something such as, will it stop in time? Will it stop in time? And it tells you that before it's going to hit the boundary, it only has 7 seconds of room to move. You would most likely solve that problem for t, and if you get something more than 7, it takes more than 7 seconds to stop, and therefore it's going to hit the wall. If it takes less than 7 seconds, it's going to stop early enough, and it won't hit the wall or the boundary. I'm trying to give you guys an idea to see how you're not going to be directly asked, what is the position? What is the velocity? What is the acceleration? What is the time? You're not going to be asked the question that direct in this course. Okay? Is that clear what I'm saying? So we need to break down what's actually being asked in the problem. Let's look at a couple more examples. Example 4 says the following. A person pushes a stroller from a velocity of 3 meters per second, uniformly accelerating at a rate of 0.5 meters per second squared. What is the velocity of the stroller after it has traveled 4.75 meters? This is a direct question this time, right? This is like a part 1 on an AP exam or a multiple choice type problem. I would not give you this problem on a part 2 quantitative because it's too easy. It's too easy. Why do I say it's too easy? Why is it too easy?
Because one of the 3 standard equations we had was literally d squared equals this.
And what are we trying to find here, Jack? So this kind of a question says, what is the velocity after traveling a certain distance? So we're using either one of 2 equations. Either we're using this first equation, which I can clearly see I can't use. What's missing? What do I not have in the problem that I'd have to use in this equation? time. Time is not given in the problem, so I can't use the first equation. And then the other option here, v squared equals v0 squared plus 2a delta x. Well, that equation is useful here because we do have all the information. So as Jack noticed, this is a plug and chug. You're going to hear me use that phrase all the time. Plug and chug, right? Remember that?
Yes.
And I don't mean chugging alcohol, ever. I don't mean that. I mean chug through the problem.
Chug vinegar.
So, vinegar, that's going to kill you someday. Be careful with that. Actually, I'll talk more about that later.
Okay.
I've got a funny story about that. Yeah, vinegar. I know people that did chug vinegar before.
Imagine, yeah.
Actually, were you in the tasting? Who came to the tasting thing? Remember Mr. Scoville?
Yeah, it was me and Princeton.
He had a student who did that once and actually chugged vinegar and had acid like burning his esophagus. Yeah. That's why that day he told you guys that don't chug the vinegar or don't drink a lot of it. We did this tasting thing on the what was that? Student Life Day or whatever.
Oh, yeah.
Anyway, back to the point. Plug and chug. What it means is plug into the problem and just go through the calculations. There's no algebraic work needed. It's a plug and chug. You literally plug the numbers in and go through it. So we get the following. It says, a person pushes a stroller from a velocity of 3. So that means that 3 is the initial velocity. That's our givens up here. It then says uniformly accelerating it. There's your acceleration. Now, what if I didn't say uniformly accelerating it? What if I said, while it increases its velocity at a rate of? What would be the indicating factor to you that tells you that it's acceleration? Besides the word acceleration, obviously. What's the indicating factor?
Meters per second.
There it is, Isabella. Very good. Your units can be your best friends. It could also be your worst enemy. If you don't know your units, you will be very lost on problems. If you know that meters per second squared is an acceleration, that will really help you on tests. And on AP and subject tests and all that stuff. Units are crucial in physics. So there's my acceleration. It says, what is the velocity of the stroller? So we're looking for the final velocity, v, after it has traveled 4.75 meters. So that is my delta x. Do I need to write x0 is 0 and x is 4.75? No. I can write that. I can say my starting position is 0, my ending position is 4.75, and therefore we can figure it out. But I'm not going to write all that because it saves me time to do it this way. 3 meters per second squared plus 2 times 0.5 meters per second, that quantity squared, second meaning not the unit, or not the number, times 4.75 meters. That will give me v squared. I don't know what that is when I get v squared. Can somebody give me that calculation for v squared? Before you take the square root. 13.75. And what's crazy is, look at the units. Here's the units. Have you seen this unit ever? No, right? Makes sense you haven't seen it because it's velocity squared. So how are you going to get the velocity? Take the, and you're going to square the units also, aren't you? So what are your final units going to be? Meters per second. Meters per second. Okay, that's why those units look a little bit funky halfway through the problem. Now take a look at what I've written. Did anyone else write that by any chance? And be honest with yourself. If you didn't, write a note. Plus or minus with every single square root you take in this class. If you forget a plus or minus, you will lose credit. Because the minus and the plus have physical significance. In this problem, my answer turns out to be, again, approximately plus or minus, this is 3.71 meters per second. That's what it turns out to be. But please, people, tell me, which answer will it be? Will it be positive or will it be negative? What do you think? Use the context of the problem, use logic, use common sense. You don't really need math to answer this question. Will it be negative 3.71 meters per second after it's accelerated from 3? Or will it be positive 3? See what I did there, right? You all pick up on that? Yeah, very good. Regina, tell us, what is it going to be? Because what are we doing in this problem? We're gaining velocity. We are accelerating. Very good. And I could lose velocity if I were doing what again? Yeah, I could lose, so technically I should say speed. I could lose speed if I were decelerating, but I could lose velocity also if my acceleration were negative. But is it? It is not. So I know that if I start with 3, my answer has to be in general, positive. What else? Greater than 3. If I start at 3 and I'm only getting faster, the answer's got to be more than 3. So negative 3.71 is not reasonable. So although we have both answers there, we choose 3.71 as our final velocity. Okay? So again, physics involves math, but it involves a ton of logic. Right? The logic behind this problem is what tells you that it's a positive and not a negative result. Okay? I want to give you a couple minutes to do example 5 with the person next to you, but then I want to get into example 6 today. So please spend at most, and I'm going to time it this time, 3 minutes. 3 minutes. Givens, equation, and then solve. 3 minutes should be enough for a problem like this, right? That's 3 minutes right now, just so you know. You're at 3 minutes. Check on the board with me at least if you see if you're on the right track, please. Again, I tried to color code here so you can see what part of the problem means what. Try to find a formula that has all of those in the formula, and one of them is
And then you use that to solve.
All right, pause where you are. If you're still talking, please pause for a moment. Take a look. All right, so several things we want to talk about. First, I define delta x to be 28. And that might be misleading at first because the one formula of delta x, right, is the v squared equals v squared plus 2a delta x. But we're not going to use that formula because we're missing v. V is the missing variable. And the only formula that doesn't have v in it is this one. So we have to use this. Now, what does delta x mean really? It means that x0 is 0 and that x final is 28. So I could set this to 0. This will become 28. Initial velocity was 0 because it was from rest. So that's 0. And then I have this. So look at what my formula reduces to. This is a very, very classic formula to see. When we get to vertical motion, we do what are called free falls. When I drop an object, its initial velocity is going to be 0. We're going to see this formula over and over and over again. Now, I would recommend, because it's such a simple formula when you simplify it, to solve for t algebraically. Multiply by 2, divide by a, and then take the square root. And that's our solution to this problem. Yes, we're going to plug in numbers. I get it. And that's our solution right here. This is the solution. We'll get a specific number to this specific scenario by plugging in. But that's our solution. Now, because it's time is only going to be positive. So when you take the plus or minus here, the minus doesn't actually matter for this circumstance. But yeah, time is never going to be negative in these problems. So when you get a negative possibility for time, you can rule that one out actually. Whereas velocity, as we saw in the last problem, can be negative. So the square root, when you're solving for velocity, needs to be considered as plus or minus. When you plug in 2 times 28 divided by 2.4, all square rooted, you're going to get approximately 4.8 seconds. Okay, approximately 4.8 seconds. I'm not trying to rush you. I know you guys have that, but I do want to look at the next example before I stop and look at the lab. That's why I wanted to get to the end of this one. But again, the problem, I know it's crazy to think, oh man, 3 minutes, that's not much time. When you get to the test, 3 minutes is actually enough time for sure. Like when you're doing the quantitative problems at the very end, you're going to want to limit yourself in time. Because if you spend 6 to 10 minutes per problem, and you have 5 problems in quantitative, that alone is going to take you 45 minutes. And then you've got no time left for multiple choice and short answer. So the reason you practice so much in physics, the reason your homework seems pretty extensive when you look at the number of problems, right? You're like, wow, it's a lot of problems, isn't it? It actually is a decent amount. It's so that you practice more. I'm only so quick at this because I've taught this course for 9 years, because I took this in high school and in college. That's the reason it comes naturally. So for you guys, the only way this course will get easier, for quantitative especially, is to practice, practice, practice. That's why you have homework. That's why you have problem sets. And I know I'm wasting time by saying this right now, but it's that important for me to say it, that I would spend that time saying it. Okay, so your practice means a lot. And practice does not mean, again, you hit the roadblock and you give up. That is not practice. That is giving up on stuff. Okay, if everybody gave up on stuff, you never accomplish your goals. You've got to find your ways around the spots in the problem where you get stuck. Maybe that's seeing me. Maybe that's asking M. Maybe that's working in a group on your homework. You should absolutely do that. Yeah, you've been encouraged your whole life. Do your own work. Don't cheat. Don't copy. I'm not saying to copy or cheat, but work in a group on homework problems. Come here. I've had a couple of you coming in regularly after school, which is awesome. Every Tuesday and Wednesday. You don't have to come for office hours. Just come and hang out and do homework problems together in a group. It facilitates a good group think when you're there together. Or maybe go to the library and do it in the Mix Center or the Module Center or whatever. Somewhere though, but work with other people. It will help you a lot with these types of problems. Now, the last question for today, the last one, is the Arthur-Betty problem all over again. Okay, it's the same problem though, which is nice. I've just changed it up a bit to add acceleration and to say that they start at different times now. So I'm just trying to change things a little bit. Here's what I think I'm going to do. Do I want to do that first? I'm going to pause. So let's quickly read it and talk it through. I know we got a minute left. Give me an extra spare, like 3 minutes. Trust me, I need to get somewhere and I'm giving you this time right now. Betty starts walking toward Arthur when they're 120 meters apart. Pretty much the same problem as your test so far. Arthur starts, though, 8 seconds after Betty. That's different. Arthur starts 8 seconds after Betty. Start thinking already how that's going to affect the problem. And has a constant speed of 4.5 meters per second. While Betty, though, has an initial speed of 2 meters per second, but accelerates uniformly at 0.2 meters per second squared. Now, part A is what we did on the test. From the time of, in this case, find when the time when they meet. Here, from the time that Betty starts walking, because they start at different times, how long does it take for them to meet? And part B is new. At what position do they meet? And make sure to give a reference point, like from Arthur's starting point or from Betty's starting point. So what I want to do to start this problem is actually not list the givens, but draw a diagram first. The diagram is more important here, actually, because the givens can show up wrong, and I'll show you how. So let's start, and I'm going to start this problem, and I'm going to be consistent with my notes right now, and I chose that Arthur in this problem started on the right and Betty started on the left. So I'm going to start, give me another minute again, please. I'm going to start with Betty over here and Arthur over here. And the reason I start by doing that is because now I need to think about, does anyone have a game or a meet? Go. If you have a meet, you guys got to go. Sorry about that, the two that have that. Good for reminding me there, Valentina. So what I notice is that Betty starts walking toward Arthur. So Betty's velocity initially is 2 meters per second. And I'm going to make that positive because in order for Betty and Arthur to meet, they got to walk together. So what is Arthur's velocity going to be in this problem? Negative. Arthur is going to walk left. So the initial velocity of Arthur is going to be negative. Now, I also want to denote, it'll be in the video, you guys can look at it later. I also want to denote the positions. Betty's initial position is the origin, what we're calling the beginning. So let's call that 0. So what will Arthur's position be? What will Arthur's position be? 120. Now, one more piece of info. Betty accelerates, Arthur doesn't. Sorry, 2 more pieces. We're going to get to the piece in a minute. So Betty has acceleration, and that's 0.2 meters per second squared. Arthur does not have acceleration. So what can we say about Arthur's velocity if he doesn't have acceleration? So therefore, I could also just write this. Take a look at what I just added. Instead of initial velocity of Arthur, I could call it a constant velocity for Arthur. Same thing, no change there.
Just for the time part of the, are you going to get to that?
Yeah, I'm going to get to that right now.
Well, when you do negative or?
Yeah, we'll get to that actually. Let me show that. So, here's how I want you to think about it. The problem says the following. Arthur starts 8 seconds after Betty. So if Betty took 20 seconds, how long will Arthur take? 12. You take away 8, right? If Arthur, though, if I said Arthur took 15 seconds, how many seconds would Betty take? 23. Be careful what we said. So, Arthur, again, in this problem, starts 8 seconds after Betty. So here's how we write it. We say, okay, Betty's time, I need a variable, here we go. Betty's time we'll just call t. But the time it takes Arthur, we're going to denote as what? T minus 8. Why t minus 8 for Arthur here? Why t minus 8 for Arthur? What are we thinking logically when we do this? What are we thinking? Isabella, go ahead.
Betty's time minus the 8 seconds.
Yeah, and that's why I asked Caroline to answer that question. I said, you know what, if Betty takes 20 seconds, how long will it take Arthur? She was like, oh, 12. And I said, how'd you get there? Subtract it. That's the key to this problem. The time it takes Betty is 8 seconds more than Arthur. So, Moro, I could also write t plus 8 here and just call this t. Because again, Betty is 8 seconds more. So you could call this t plus 8 and call this t. Or call this t and call this t minus 8. Now, the last part, I'm going to leave you with this. I'm not going to have you do it together because I know we are over time already. The last part is this. When they meet up, what part of the problem do you know is equivalent when they meet up? When they meet up, what is equivalent? Their position, not their time in this problem. In the last problem on the test, when you guys did it, the time took the same, the position was the same. The time is not going to be the same here because Betty and Arthur start 8 seconds apart. But yes, the positions will be the same. So our governing to start is that XB equals XA. Let me write that a little bit closer. The position that Betty is at will be the position that Arthur is at. And then we just plug in our formula for position. And it sounds like, oh, just do that. Like it's no big deal, Mr. Howell, right? But the formula is the same one we've been using. It's right here. So take a look. When it's Arthur has no acceleration, so that drops off. Arthur has initial position, so this stays. Arthur has initial velocity, so this stays. But then for Betty, what drops off? What drops off for Betty? Of this equation, what drops off for Betty? Look at the formula, look at under Betty's name. What's a zero there, Seth? No position for Betty because she starts with the origin. She's got acceleration, she's got initial velocity, so Betty's equation drops off and looks like this. Arthur's equation again drops off here and looks like that. So the equation that you're going to write here is going to be for Betty again with no position is simply going to be V0 Betty times the time it takes Betty plus 1/2 the acceleration of Betty times the time it takes Betty squared. So again, I'm just using a ton of subscripts, which makes this look harder because it's B everywhere. But this equation is simply the equation number 2 we derived today in class. And then Arthur will be very similar. Arthur will have an initial position, but Arthur will not have acceleration. Okay, there's no acceleration part for Arthur. So again, we're missing the 1/2 AT squared for Arthur. We're missing the x0 for Betty because those pieces are equivalent to 0. At this point, it seems tough, but everything is given. Everything is known. You can plug in everywhere. TB is just T. V0 is 2. A is 0.2. TB is just T. Next, x0, 120. VOA, negative 4.5. TA is T minus 8. So you're going to get an equation that seems difficult because it's all in terms of T. It will be a quadratic. How many answers does a quadratic yield? 2. You will reject the negative, you will keep the positive. Once you get the answer for part A, you can do part B. Now, over the next couple of days, over the weekend, you have to get your lab in by next week on Tuesday. Your homework for this, if I recall, is not due until next Friday. Am I correct by that? Yeah? So, what I'd like you to do over the weekend is definitely do the lab, finish this problem, and consider starting the homework. But again, this homework is not due until next Friday. And note for number 31, I said, see page 32 for help. You can ignore that and be struggling, or you can listen and do that. Okay, guys, good job today. Really good. Please keep coming for office hours when you need help. This